Hello. After having explained the basic architecture and addressing modes of the ARM processor in the previous lectures, this and subsequent video lectures will explain the instruction set of the ARM processor. The current lecture explains the data transfer instructions of the ARM processor in details.
Let us study the ARM instructions. The instructions of ARM can be classified into different categories depending upon their functions. Data transfer instructions, data processing instructions, branching instructions, and some instructions which perform some special operations. Data transfer instructions. These instructions are used to transfer the data between CPU registers or register bank inside the ARM processor and the system memory, and therefore the instructions coming under this category are only load and store type of instructions. Load instructions load the data from system memory to the register in a register file, and store instructions store the data from register file to the system memory. Single register transfer instructions. Let us consider this instruction. It is either load or store followed by a register and the memory address. In case of a load instruction, this is the destination register in which the data from the memory will be loaded, and in case of a store instruction, this will be the source register. The data from register will be stored into the memory. The address field specifies the address of the memory location where the data is to be stored or from which the data is to be loaded. This instruction can load or store a 32-bit number or a word. It may be signed or unsigned between memory and the register file. These are some examples. For example, if you consider LDR R12 followed by this address. Here this is one of the registers of the register bank, and in the square bracket the memory address is specified by using one of the different addressing modes available. In this instruction, the address is generated by adding this number to the base register R14, and that works as a memory pointer. It points to a memory location, and data from the memory location is loaded into register R12. Similarly, this instruction stores the content of register R2 to the memory location pointed by the address in register R1. So R2 is transferred to the memory location pointed by R1. This instruction can transfer only one word at a time. Similarly, there are some instructions which can transfer a single, either a byte or a half word, 8-bit or a 16-bit half word, between memory and the register file. That byte or half word may be signed or unsigned. Let us consider this pair of instructions. This is for loading a byte, unsigned byte particularly, from memory to the specified register, and this is the instruction for loading a half word from a memory location to the specified register. Both these instructions, they work on unsigned numbers. Whenever a small size number like a byte or a half word from memory is copied into a 32-bit register, for example, when a byte is copied, the lower 8 bits of this register will be occupied by that byte, and all the remaining bits will be loaded with 0. Similarly, when a half word is copied from memory to a 32-bit register, lower 16 bits will be occupied by that half word, and remaining the higher bits will be loaded automatically by 0. So that's how a byte or a half word unsigned can be copied into a 32-bit register. Next pair of instructions is for signed byte or signed hop word. These instructions, they load a signed byte from memory to a 32-bit register or a signed hop word from memory to a 32-bit register. This operation requires the process of sign extension. There is a sign extension block in the ARM processor which is used by these instructions. So for example, whenever a signed byte is copied from memory to a 32-bit register, lower 8 bits of that register will be occupied by that byte, and all the higher bits of that register will be loaded by the sign bit of that number. If the number is negative, it will be loaded by 1. If it is positive, then the sign bit is 0 and all the higher bits will be loaded by 0. Okay, so this is what is called as sign extension, and that is required to be performed during execution of these instructions. So therefore there are separate instructions for signed byte or hop word, loading signed byte or hop word into a register file, and separate instructions for unsigned byte or hop word. Now while these instructions, next pair of instructions are for storing the content of these 32-bit registers to the memory, particularly storing a byte to the memory or storing the hop word to the memory location. For storing a byte or a hop word from a 32-bit register to the memory location, for example, for storing a byte from this 32-bit register to the memory location, the lower 8 bits of this register are simply copied into the memory location. All the remaining bits of this register are simply ignored. Similarly, in case of a hop word, low 16 bits are transferred to the memory location, all the remaining higher bits are ignored. Here no special processing is required during storing of the data from a 32-bit register to the memory location, and therefore these instructions are applicable for signed as well as unsigned numbers. But for load operation, separate instructions are available for loading unsigned byte or hop word, and separate instructions are available for loading signed byte and hop word. The instructions that we have discussed up till now are capable of transferring only one word or one byte or one hop word between the register, single register and memory. Multiple register transfer instructions. Now there is an instruction which is capable of transferring content of multiple registers from the register bank to the memory or from memory to the register bank. So the instruction is load multiple or store multiple. The list of registers is given here. Contents of these registers will be transferred between the memory and these registers. Register Rn holds the start address of the memory location from where the data will be loaded into these registers, or from where the content of these registers will be loaded into the memory. So this simply holds the start address of the memory area. In addition to this, this instruction contains two fields, condition field and addressing mode field. Condition field, this field makes this instruction conditional instruction. Actually, all the instructions of the ARM processor are conditional instructions. You can put one of these conditions typically at this place, for example, equal, not equal, less than, greater than, less or equal, and so on. Okay, so when this condition is put here, then the instruction will be executed only when that particular condition is satisfied. For example, a compare type instruction, for example, a compare type instruction can be put just before this instruction and it will be followed by this. So when the compare instruction compares the two numbers, then depending upon these conditions, only when this condition is satisfied, whatever condition is mentioned here, only when that condition is satisfied, then only this instruction will be executed. So that makes this instruction conditional instruction. Of course, there is one instruction, one condition here which is always condition. If I put always condition here, then this instruction will be executed always. In other words, it will become unconditional instruction. Next field is addressing mode. There are 4 addressing modes: increment after, increment before, decrement after, and decrement before. One of these addressing modes is actually used by this instruction during this data transfer. The meaning is simply like this: when, for example, if the content of the registers are to be transferred to the memory location, to the memory, then if you choose addressing mode increment after, then the address which is given here, initial address, will be incremented after storing of every register to the memory location. It will be incremented after the storing of the number. Increment before, if increment before is the addressing mode, then address will be incremented first, and then the content of the register will be stored into the corresponding memory location. So that is how increment after, increment before, and decrement after and decrement before. Okay, so in these two cases, the address in this register will be incremented after or before transfer of every word, and in these two addressing modes, the content of this address register will be decremented after or before transfer of every word. Secondly, you can see is that see what you see here is that the address will be either incremented or decremented by 4 for transfer of every word. For example, if you transfer single word, then this will be incremented by 4 or decremented by 4. This is because the main memory or the system memory is byte oriented. Every location holds only 1 byte of data, and therefore when you transfer 32-bit number from a register to the memory, it will occupy 4 memory locations, and therefore after transfer of every word, the memory pointer should be incremented by 4 or it should be decremented by 4 for transfer of single word, and therefore the memory pointer will be updated depending upon this equation, depending upon how many words you are transferring from memory to register or from register bank to the memory. The list of register field can be given like this. You have to mention the list of registers which are to be transferred to the memory or to which the content of the memory is to be loaded. It can be given like this: R2-R6. So it means all the registers between R2 to R6 will be transferred to the memory, contents of these registers. Or also you can give the list of registers in this form, say R2, R5, R8-R10. So here you are giving the registers discretely, and then there is a continuous range of registers R8 to R10. So you can use one of these methods or this kind of methods to give the list of registers from which the data is to be transferred to the memory. Now let us discuss what is meant by block copy addressing and stack addressing. If you consider the execution of this instruction, it shows that this instruction copies a block of data from registers to the memory or from memory locations to the registers. So this is one view to look at this operation, and there are 4 different addressing modes associated with that. So this is what is called as block copy addressing view. There are 4 addressing modes, and here what you can see is that the address register can be any one register from the register bank. Okay, it can work as the memory pointer. Okay, so that is the block copy addressing view. You can look at this operation in a different angle. Whenever contents of these registers are saved on the memory, in the memory, it is like pushing of register data to memory. Or whenever you copy a block of data from memory to these registers in the register bank, it is like a pop operation, and therefore this operation can be viewed like a stack operation. So that is what is called as stack addressing view. In the stack addressing view, of course, the memory pointer should be always the stack pointer, because stack is pointed or it is handled only by stack pointer. Therefore R13 register can only be used when you are observing this operation through this view. Now there are different types of stacks. There are different types of stacks which are listed here: full descending stack, empty descending, full ascending, empty ascending stack. Each of this type of stack is associated with these addressing modes, one of these addressing modes. So there is a 1-1 correspondence, 1-1 relation. Each addressing mode is associated with one of these type of stacks. Let us see how the relation is there between these addressing modes and the type of the stacks. This diagram shows the different types of stacks: full descending, empty descending, full ascending, empty ascending. Okay, let us consider this type of stack, which is full descending. You know, stack is a memory area which is used for temporary storage of data. For example, suppose initially your stack pointer may be here. So this shows the beginning of the stack area. Initially your stack pointer is here. When you push or when you save first operand on the stack, then first of all the stack pointer will be decremented and then the number will be stored. Every time you push the next number, the stack pointer is decremented and then it is saved. It is decremented and it is saved. And so what you see here, that during saving the data on the stack pointer is decremented. That's why this is called as descending stack. Secondly, because of this operation, at any instant of time you can see that your stack pointer will point to the last field location, last full location on stack, and that's why this is called as full descending stack. Stack pointer points to the last full location on the stack, so it is full descending stack. That's why when you save the data, when you are saving the data and when you are looking at this operation through stack view, then the instruction which is typically used is like this: store multiple, and then you mention the type of the stack, full descending, and then the data will be stored in this manner. When you look at this operation through block view, then you can see that suppose you imagine that these numbers are it's a block transfer of block of data from register to the memory. Then what is happening here is that memory pointer is initially here and then it is decremented first and the first number is stored. Okay, and therefore you can see that the memory pointer is decremented before the number is stored. Memory pointer is decremented before the second number is stored. Okay, so that's how decrement before is the addressing mode which is being used here if you consider this operation as a block view operation. And therefore store multiple and followed by addressing mode, decrement before, this becomes the mnemonic of the instruction which treats this operation as a block transfer type of operation. So what you see here is that these two instructions are having different mnemonics, but they are performing same operation. Simply the mnemonic depends upon the view, whether it is a stack view or whether it is a block view. Both are equivalent instructions. Similarly, you can go for another type of stack. Empty descending stack. So what you see here in this case is that after initially stack pointer may be here. So when the first number is saved, it is saved first and then the stack pointer is decremented. Second number is saved and the stack pointer is decremented. Third number is saved and the stack pointer is decremented. So because of this, stack pointer is decrementing after storage of every number, so it is a descending stack. And because of this, you can see that the stack pointer points to the first empty location on stack. So it is called as empty descending type of stack. Okay, so this is the corresponding instruction: store multiple, empty descending. If you look at this operation through block view, then you can see that when the numbers are being copied from register file to the memory, then suppose initial memory pointer is here, then the number is saved first and then the memory pointer is decremented. Okay, so this is what is the operation is: decrement the memory pointer after the storing of the byte, storing of the data. Okay, so every time the data is stored and then the memory pointer is decremented. So here the memory pointer is decremented after the storing of the data, and therefore decrement after is the addressing mode associated with this type of stack, and therefore the instruction under this block view will be store multiple descending decrement after. Okay, so again you can see that these two instructions are equivalent to each other. So in this manner you can look at full ascending stack and empty ascending stack. So here we can see that in this case your stack begins from this, and initially stack pointer is here. So after storing of every number, the stack pointer is being incremented, and therefore it is an ascending stack. Then you see that when the stack pointer is here and first number is to be stored, then it will be incremented and then the number is stored. So because of this, what happens that at any given instant of time, the stack pointer will point to the last full location on the stack, and therefore it is full ascending type of stack. So store multiple full ascending is the mnemonic of the corresponding instruction. If you consider this as block transfer, block data transfer, then when the data is being transferred from register file to the memory, initial memory pointer is here, and then you can see that the address is incremented first and then the data is stored. Okay, so it is address is incremented before the storing of the data. Address is incremented before the storing of the data, and therefore increment before is the corresponding addressing mode in this view. So again these two instructions are equivalent. Okay, now you go to the empty ascending stack. Once again the stack is ascending stack. Initial stack pointer is here. After every transfer of a byte of the word or the number, the stack pointer is incrementing, so it is ascending stack. And because of this, what you see that at any given instant of time, the stack pointer points to the first empty location on stack, so it is empty ascending type of stack. So store multiple empty ascending. Okay, that is the stack view mnemonic. In the block transfer view, we can see that initial memory pointer is here. So when the first number is stored, the number is stored and then the address is incremented. Number is stored and then the address is incremented. So the address is incremented after the storing of the number, and therefore increment after is the addressing mode associated with this operation. So in the block view, the mnemonic of the instruction is store multiple increment after. So once again these two instructions correspond to the same operation. So what you see here is there are different types of stacks, and you can refer to the stack by using appropriate mnemonic. So this is about saving of the data, and therefore the instructions are store type of instructions. Similarly, when you want to retrieve the data, these are the load type of instructions, and corresponding stack view and block view mnemonics are as shown in this table.